Standing at 828 meters, the Burj Khalifa is a vertical frontier that redefined engineering. To anchor 500,000 tons into shifting sand, engineers used a mat foundation with 192 deep-seated piles. Its buttressed core system utilizes a Y-shaped footprint to provide maximum structural rigidity and lateral support. The tower's stepping tiers confuse the wind, breaking up air vortices to prevent dangerous swaying at extreme heights. 26,000 high-performance glass panels act as a thermal shield, reflecting heat to keep the interior cool. A testament to human ingenuity, the Burj Khalifa remains a masterpiece of modern engineering.
After the devastating North Sea flood of 1953, the Netherlands vowed, never again. They didn't just build dikes, they re-engineered an entire coastline. The Delta Works is a 13-part defense system so massive. It shortened the Dutch coastline by 700 kilometers. This was not just construction, it was a total reimagining of Dutch safety. A wall of water met with a wall of human ingenuity. The crown jewel is the Eastern Schelp Barrier. Initially planned as a solid dam, engineers pivoted to protect the ecosystem. They chose a solution that allowed the tides to flow, preserving life. They built 65 massive concrete pillars, each weighing 18,000 tons. These support 62 steel gates that stay open for marine life, but can slam shut in 75 minutes when a storm surge threatens. When nature strikes, the system responds with absolute precision, closing the gates, protecting the land. But the ultimate marvel is the Macelamp Barrier. It consists of two hollow steel arms, each as long as the Eiffel Tower. When a 3-meter surge is detected, these wings float into the river, fill with water, and sink to the bottom, creating an impenetrable wall. This guardian protects the port of Rotterdam, the heart of European trade, a sleeping giant always ready to defend. While most countries build for 100-year storms, the Delta Works is built for a 1-inch to 10,000-year event. It is the gold standard for climate resilience, the ultimate proof of human will. Human 1, Ocean 0, a victory for engineering over the elements. This concludes our journey through the world's engineering marvels.
The James Webb Space Telescope, the golden eye of humanity, is a marvel of modern engineering designed to peer into the dawn of time. But before it could see the stars, it had to survive a journey inside a rocket only 5 meters wide. This required an origami feat. Engineers designed a 6.5-meter primary mirror that could fold perfectly, like cosmic origami, to fit within the narrow confines of its launch vehicle. Once in space, the deployment was a high-stakes dance involving hundreds of single-point failures that all had to work perfectly. It was the most complex deployment ever attempted in space, a testament to human precision and mathematical certainty. Against all odds, the golden eye opened, ready to capture light that has been traveling for over 13 billion years. To capture that ancient light, the telescope's mirrors had to be made of something extraordinary, beryllium and gold. Beryllium was chosen for its incredible strength-to-weight ratio, allowing the mirrors to remain stable in the extreme cold of space. Each mirror is coated in a layer of gold just 100 nanometers thick, about the width of a human hair. Why gold? Because it is exceptionally efficient at reflecting infrared light, the very light emitted by the first stars and galaxies. This golden coating allows Webb to see through cosmic dust clouds, revealing the hidden secrets of the universe's infancy. It is a masterpiece of material science, where every atom is placed with absolute, scientific precision. But to detect that faint heat, the telescope must remain frozen. This is the job of the massive, 5-layer sun shield. Made of a material called kapton, these layers are separated by vacuum gaps to prevent heat from conducting through. On the side facing the sun, temperatures can soar to a blistering 85 degrees Celsius, hot enough to boil water. Just inches away, on the shaded side, the telescope rests in a deep freeze of -233 degrees Celsius. This massive temperature delta, over 300 degrees, is what allows Webb-sensitive instruments to function. Without this shield, the telescope's own heat would blind it to the very stars it was built to find. Where do you put such a sensitive machine? Not in Earth's orbit, but 1.5 million kilometers away. This is the Lagrange point 2, a unique spot where the gravity of the Sun and Earth balance perfectly. At L2, the telescope can stay in a fixed position relative to Earth, always keeping its back to the Sun. This allows for permanent, uninterrupted observations of the darkest corners of our universe. From this lonely, stable outpost, the Golden Eye watches, waiting to tell us the story of where we came from. A triumph of engineering, science, and the human spirit. The James Webb Space Telescope, our window to the infinite.
Japan is a land of islands and intense seismic activity. To link the city of Kobe to a Waji Island, engineers had to cross the Akashi Strait, a stretch of water 4 kilometers wide with currents like a washing machine, and winds that reached 280 kilometers per hour. A standard bridge wasn't enough. They needed a record breaker. They needed to build something that could withstand the very earth moving beneath it. In 1995, while the bridge was under construction, the devastating 7.3 magnitude Kobe earthquake struck. The epicenter was just miles away. The bridge towers were already standing. And the shock was so powerful it actually moved the towers 1 meter further apart. Engineers didn't panic. They simply recalculated the entire design and lengthened the central span mid-construction. It was a feat of adaptability that redefined the limits of engineering. Standing over 280 meters tall, these pillars are the backbone of the giant. Deep beneath the waves, the foundations hold firm against the current. The new span was set, proving that engineering is as much about flexibility as it is about strength. The bridge is held up by 300,000 kilometers of wire, enough to circle the Earth 7.5 times. These cables are made of a new high-strength steel that can withstand immense tension. To stop the wind from shaking the bridge to pieces, they installed tuned mass dampers, giant weights that swing in the opposite direction of the wind to stabilize the structure. It's an invisible battle against the elements, fought every single second. Completed in 1998, the Akashi Kaikyo Bridge can survive an 8.5 magnitude earthquake. It is a $3.6 billion monument to human resilience. When nature moves the goalposts, we build a longer bridge. From the clouds of Dubai to the deepest reaches of space, we've seen what happens when human ingenuity refuses to accept impossible. These marvels were built to stand for centuries. But as our world changes, the challenges are getting bigger. The question isn't just how we build, but how we survive. In our next series, we are leaving the past behind. We're exploring the mega projects of tomorrow, the tech that will save our planet and take us to the next one. We're looking at self-sustaining Mars colonies and magnificent underwater metropolises designed to withstand the rising tides. Don't miss the first drop of our new series. Hit subscribe and turn on the bell. Stay ahead, stay profitable. I'll see you in the next one.